What would happen if you fell into a black hole? If you'd asked Albert Einstein, he would have told you that according to his general theory of relativity, you'd be sucked into the black hole's singularity, the point where space-time curves steeply inward and all the laws of physics seem to break down. After that, nothing can escape. In the 1970s, Stephen Hawking took a semi-classical approach to black holes. Bringing together quantum theory and Einstein's relativity, he proved that black holes emit a small amount of heat that eventually causes the black hole to evaporate. Still, according to Hawking, if you fell into a black hole, you and your particles would be lost to the universe forever. This is Don Page. He was a postdoc with Stephen Hawking, where they became friends, despite the fact that they ultimately landed on either side of one of the most controversial debates in modern physics.
I looked at Hawking's argument and I became not convinced by it.
Hawking's work implied that black holes violated a central principle of quantum mechanics, called unitarity, which says that the present always preserves information about the past. So how could it be possible that black holes destroy information? This became known as the black hole information paradox, and for decades, it made physicists queasy. According to Page, if you were to fall into a black hole, you wouldn't be gone for good. Particle by particle, the information needed to reconstitute your body would reemerge.
Well, it would be highly scrambled by the black hole. It'd be much worse than even, if you just cremated the body and it turned into smoke and ashes. But, another analogy is if you burn up a book and you have all the ashes, the information is still somewhere in the universe, we believe.
The key to understanding why the information is preserved lies in a process called quantum entanglement. When black holes emit radiation, that radiation maintains a quantum mechanical link to its place of origin. If you tried to measure the radiation or the black hole separately, the information would look random. But when you look at them together, they exhibit a pattern.
If somebody took a coin and cut it in half, and then you sort of shook it up and put it in two envelopes and sent it off to two people, then of course there would be what we call correlations in it. If one person gets a head, the other person would have tails. And this quantum entanglement is like that, except it's an even more subtle.
This is the Page curve, which he created to track changes in the entanglement between a black hole and its radiation as it ages. The degree to which the information is entangled is called its entanglement entropy. At the start of a black hole's life, its entanglement entropy is 0, since it hasn't emitted any radiation. And at the end, its entanglement entropy is 0 again, since the black hole has evaporated. But in between, as radiation trickles out, the entanglement entropy grows. Page showed that, in theory, information can escape from a black hole. In a series of groundbreaking papers, physicists have shown that the entanglement entropy of black holes really does follow the Page curve.
These calculations give more evidence that indeed the information does come out, but the details of how that actually happens and still remain to be understood. And of course it raises the picture that maybe space-time itself is not fundamental. Maybe there's something deeper than space-time, and maybe the basic quantum description will involve something that's not space and time. So I think there'll be parts of the puzzle, I think, that'll persist for many more decades.